So now we're at 6.3. I am on page 336 and I want to do an intro to 6.3. It's called the central limit theorem. It's a really cool idea and it's a really cool event that happens in statistics. I'll read a whole lot to you. If we were in class, you would get to do it. So read along or get somebody in your family to read with us. But here we go. In addition to knowing how individual data values vary about the mean for a population, statisticians are interested in knowing how the means of samples, like you might have 1,000 participants and you do a mean of 20 of those and then another mean of 20 others and another mean of 20 others. Knowing how the means of all of these samples of the same size, like a 20, a 20, a 20, taken from the same population vary about this population mean. It's really cool what happens. So suppose a teacher selects a sample of 30 adult males and finds the mean of the measure of the triglyceride levels for the sample subjects to be 187 milligrams per deciliter. Then suppose a second sample is selected and the mean of that sample is found to be 192 milligrams per deciliter. And then they keep going with this process for 100 samples, 30 adults at a time. So what happens then is that the mean becomes a random variable and the sample means constitute a sampling distribution of sample means. So getting ready for our upcoming test, I am going to make a video and I'm going to mention things like vocabulary. So this is good to have on a card or highlight or sticky note or something, that a sampling distribution of sample means is. It's a distribution using the means computed from all possible random samples of a specific size, like if we use 20, all of them have to be 20, from that population. A lot of reading, so you may want to start and stop this video or just keep listening and keep underlining. If the samples are randomly selected with replacement, the sample means for the most part will be somewhat different from the population mean. The whole reason we're even doing all of these means is to try to find out what's normal, what is average. These differences are caused by sampling error. Sampling error is just the fact that we used a sample. It's the difference between the sample measures and the corresponding population measure due to the fact that we used a sample. And it is not a perfect representation of the population. But in statistics, you know this, you take account for it, you deal with it. When all the possible samples of a specific size are selected with replacement, you'll notice some key words here, from a population, the distribution of the sample means for a variable has two important properties. Huge, underline, highlight, star. I even have a wow on this one. Here's a property when all of this stuff is done. And remember, the title is called Central Limit. Everybody's trying to get to the central, the center. Number one, the mean of the sample means, is going to be the same as the population mean. So if we do an average of all these little samples, it will be the same as this ominous population mean we've been looking for. Wow. I need another exclamation mark on that. Wow. The standard deviation, number two, the standard deviation of the sample means will be smaller, so that how much we deviate, how much on each side of the mean, it's going to be smaller than the standard deviation of the regular population. Wow. That means it's better, it's tighter, and it will be equal to the population standard deviation divided by the square root. Oh, whoa. It's going to be a new formula we're going to add to our card. The population standard deviation, oops, you can't see what I'm writing, divided by the square root of the sample size. Oh, no biggie. Y'all go on over with me to page 338. And on 338, I am starting right here at the note. I'm just a little bit down from the top of the page, and it says, in summary, if all possible samples of size n are taken, here we go again, with replacement, from the same population, the mean of the sample means is going to be denoted by mu sub x bar, because it's a mean of the sample, equals the population of mean mu. Whoa, whoa, and wow. And the standard deviation is going to be denoted by sigma sub x bar, and it equals to that sigma divided by the square root of n. Wow. The standard deviation of the sample means is called the standard error. Okay, whoa. The standard deviation of the sample means is called the standard error. Hence, we have a formula. Hence, grab your card. And when you look at your card, you notice where it says standard error of the mean. But it also called this something else. It said the standard error of the mean is the standard deviation. And you might want to just jot that down, that the standard error of the mean is also called the standard deviation of the sample means. You might want to write that on your card. I put a little 3 out here because earlier on the page 336, it said here are 2 properties. Number 1, it's the same as the population mean. Wow. Number 2, oh, the standard deviation is going to be called this thing right here. Oh, okay. And then, hey, sorry if that makes a loud noise when I crash into the document camera. There is a third property. A third property of the sampling distribution of the sample means pertains to the shape. And it is explained by what's called the central limit theorem. The central limit theorem. As the sample size n increases without limit, in other words, just let your brain go to infinity and beyond, the shape of the distribution of the sample means taken with replacement from a population with mean mu and a standard deviation will approach a, it happens every time, normal distribution. As previously shown, the distribution will have a mean mu and a standard deviation because it is the population mean. And to get the standard deviation, we've got to do a little bit of tweaking. So it's not just sigma, it's sigma divided by the square root of n. A little bit more. If the sample size is sufficiently large, it can be used to answer questions about sample means in the same way that we use normal distributions. The only difference is there's a new formula for z. So go back to your formula card. And looking over here, there's a new formula for z. No biggie. On the z, x bar, I can find that. I got it. Put it on your card. Actually, just highlight it on your card. Notice that x bar is the sample mean, and the denominator must be adjusted. X bar is the sample mean, and we got to do a little bit more with just dividing by sigma, and it's not just a data value, it's a mean of a bunch of data values. It's got to be adjusted since means are being used instead of just individual data values. And later you're going to hear me point out, which one do I use? Which z-score formula do I use? And it's already starting to develop because it says this one's using the sample mean. It's going to be a bit larger than individual data values. The denominator is the standard deviation of the sample means. It is important to note 2 things when you use the central limit theorem. When the original variable is normally distributed, the distribution of the sample means will be normally distributed. So if we start normal, it is normal. And that is for any sample size n. Any means any, like 5. Wow. Number 2, when the distribution of the original variable is not normal, then we have a stipulation. We got to use a sample size of 30 or more to make it normal. And you're probably still saying, wow, that's not large enough. Statistically, it works. The larger the sample, however, the better the approximation is going to be, smiley face. So this ends our introduction to section 6.3.